Hey, welcome back. So we're looking at circuit loops like this with 6 up moves and 4 down moves. And we've got a chart that calculates this denominator and the numerator. And we can see that in this case it's not an integer because 59 is a spoiler here in the denominator. So we looked at a few methods for trying to prove that every cell has some sort of spoiler. And one method we looked at was looking when x and k minus x have a common factor. And those are the cases in red here. And what we found was if they do have a common factor, we came up with an argument to show that there's no integer circuit loop. Now that leaves the white squares here, which is about 60% of the squares, where x and k minus x are co-prime. Now if you look at all these white squares over here, 2 to the k minus 3x and 3 to the x minus 2 to the x, the numerator and the denominator are also co-prime, share no factors in common. And so if we could prove that this implication, then we could show that all the white squares also have no integer circuit loops. Now, before starting to prove this, maybe it's a good idea to go make sure that it's true for all the white squares, not just the ones we look at. And if you look at the very next white square here, so that's where x equals 11 and k minus x equals 30, it's not true. So the numerator and the denominator actually share a factor in common, which is 331. Okay, so this conjecture here is not really true. But there might be other ways of dealing with the cases where x and k minus x are co-prime, and we're going to look at that later. Okay, another method we looked at was to come back to this chart and place a red block here on every square where the 5 factor is a spoiler. So that means the factor 5 is in the denominator but not in the numerator. And if we fill up this chart this way, we can rule out all of these combinations of x and k minus x, so that these are not, we know these are not circuit loops. And once we do that, we can say, okay, how about the prime factor 7? Where is it a spoiler? Well, it's also got kind of a regular pattern, and we can mark all of its places where it's a spoiler. Now we can't put anything on the 6th row here because 7's also in the numerator. Okay, so we can mark all these as invalid loops. And then we could go to the next prime, which is 11 and 13, and try to find them. And these are all places where 11 and 13 are also spoiling, so that the ratio is not an integer. And so we found out we could, show that a lot of these loops are impossible. And what happens if we keep going and we go with all of the first 1,000 primes and keep doing this? Well, we can put basically a red block on 83% of the combinations of up moves and down moves. Now the white ones are still left, and these are ones that are not covered by the first 1,000 primes. So for example, in this cell we've got 8, 1, 1, 1. That's with 4 up moves and 5 down moves. So 8, 1, 1, 1 is just hasn't swept in yet with its crazy but regular pattern, where it comes and marks this cell. And the same thing for the one under it, 16, 1, 4, 1, and so on. So what we don't know is whether, if we keep going through all the primes, whether every cell here except for the top 2 and the left is going to be marked with a spoiler, marked in red. So it could be the case that somewhere way out here there's still going to be a white square that has factors, but it doesn't, all of its factors are also in the numerator, 3 to the x minus 2 to the x. Okay, so you never know, because we've got these white squares in the top. Those are sort of like the 1 cubed plus 1 cubed plus 1 cubed equals 3, and 4 cubed plus 4 cubed minus 5 cubed equals 3. But we got to rule out that there's some huge numbers and some huge loop somewhere that doesn't appear on the small charts like the ones we're working with here. So even though we've got 83% of a proof, like we say on this channel, that doesn't mean anything until we've proved the whole thing. Okay, nice to talk to you and see you next time.